Good morning, good afternoon, wherever you are in the world, depending on your time zone. I'm Anastasios. I'm a professor of earthquake engineering at the University of Bristol and National Technical University of Athens in Greece. And I'm delighted to participate in the MIDAS Global Engineering Insights webinar. Today we'll be talking about seismic design of bridges under quite a peculiar seismic scenario that involves ground motions that are non-uniform across the supports of the structure. This is something that exists in the current code, but is not really addressed in the, let's say, necessary detail. But it has been greatly improved in the recent provisions of the new generation of the Eurocode that is to be implemented as of 2027. So I think it is very timely to talk about what asynchronous excitation is, why it is important, how it is accounted for in the design framework of the new Eurocode 8. So without further ado, let me just give you an overview of what we'll be talking about. I very much like to start with the physics, let's say the fundamentals of the problem, because if we do so, we will be able not only to learn and find out how the new Eurocode 8 addresses this matter, but I believe we'll be able to comprehend what is simple and what is more complex and what we should be doing depending on its separate design we undertake. So we'll start with some fundamental, let's say, concepts and some evidence about what asynchronous excitation is and why it is important. Then we'll go through the current provisions and the new provisions of the Eurocode 8, and then briefly we'll see some results dealing with the implementation of the new provisions for the case of a few existing bridges in Europe. Let us start by questioning pretty much a fundamental assumption that most of us are doing in design. So, there is this wide perception that uniform excitation is something that is always conservative, and therefore if we forget about the spatially variable nature of ground motion across an extended structure, it's going to be fine. This is not necessarily true, as you're going to see in this brief webinar, and if it's not true, it means that we need to do something. So the first thing we would like to challenge together is whether the common assumption that all your support points in your finite element model will be excited with exactly the same time history is conservative or not. So let's start with the definition that the Eurocode 8 is giving in the current version. Not the new generation, in the standard one. So spatial variability is defined as the situation where ground motion at different points differs, and therefore the seismic action cannot be based to the characterization of the motion at a single point, typically applied in an identical manner across all support points. So the code recognizes that ground motion is not the same. And effectively, if you simply consider any long structure, that could be a bridge, a pipeline, a buried pipeline, an above ground pipeline, anything that extends, let us say, above 100 meters or so. Take this example. There is absolutely no reason at all for ground motion to be the same from one point, let's say the support of one pylon, compared to the support of another pylon. Why? First of all, because waves travel. And as they travel, many things happen. So, can we realistically consider that earthquake ground motion is just this single TXT file that we're using, and we take it identical at all support points? Sometimes when we're doing probabilistic assessment, we say, well, you know what? I'm using a bunch of motions. There might be 100 ground motions. I have accounted for the uncertainty in the earthquake input. Well, yes, in terms of amplitude and in terms of frequency content, maybe in terms of duration, and in any other criteria I'm using for selecting ground motions. But at the same time, I have not accounted for at all by the fact that as waves travel across my structure, they do change. And this is the very topic we are discussing today. And it is easy to comprehend that waves travel, as you see in this visualization. So the minimum one could possibly consider is that even if the ground motion was the same, it would take some time. There would be some phase difference before the waves would arrive from one point to another point. Is this related to the speed of traveling of the waves? Yes, of course. Be careful, not the shear wave velocity, because we're not talking right now about vertically propagating shear waves. If we have a bedrock and all waves simply travel from the bedrock vertically upwards to the free field, then there would be no phase difference. They would arrive at exactly the same point. But because waves travel at an angle, this means that they have an apparent velocity, which is different than the Vs velocity. It's much larger, yes, but it's definitely different. And therefore, they would arrive at different points at different times. Now, apart from this time delay, they will also get reflected, refracted, superimposed, and change from one point to another. This is expressed by this equation that you see at the very top, and also the graph at the bottom left, which is called coherency. And effectively, it expresses the statistical similarity or the correlation, if you like, between different ground motions. So due to wave travel, ground motions not only arrive at a delay, they are different. And because they are different, their coherency drops with frequency and with distance. So the longer 2 points are, the less correlated they are. This is something easy to understand. And the higher the frequency they carry, the higher, the quickest the drop of this correlation, which is called coherency. This is a general rule, and this rule has been verified in various strong motion arrays across the world, in Taiwan, in Japan, in the West Coast, and in Europe. And that's exactly why different scientists are plotting, like you can see here in this chart, for a given distance. They plot coherency with frequency and start from unity, which means identical signals, and gradually this coherency drops with increasing frequency. Now, which one of these equations you're going to use, that's subjective, obviously, depends on the seismotectonic environment you're in, but whatever you use, or if you use the average of them, the notion is the same. Similarity, let's say correlation or coherency, drops with frequency and with distance. This is a fact. So there is no chance ground motions are the same from one point to another point. Of course, the $1 million question here would be, well, okay, maybe points have a different excitation across a bridge, but the response will be conservative. The response of a bridge will be reduced, and the design quantities will be reduced. And if that's the case, we don't have to worry about it. And this is actually the useless seminar of the day, because we've learned nothing and there is nothing to do about it. But that's not exactly the same, because that's exactly the case. Because, first of all, when ground motions are different, it doesn't mean that the structural response will be beneficial or will be mitigated, reduced because of asynchronous excitation. You will see examples that the global response will be very different. Why? We'll explain in a minute. But clearly, there is no safety in ignoring it. So let's say some numbers so that it is more justified. For instance, consider a case where not only waves take time to propagate, not only they are reflected and refracted and they're changing in phase and in amplitude and in frequency content, but you also have very different local cell conditions. That's an additional reason. It's an additional reason because commonly in bridges that cross valleys, the soil profile is kind of rocky or soil type A at the abutments, and then it can become, softer as you cross a valley, or even very soft and liquefiable in specific cases, which means that different points will have very different frequency contents and actually amplitudes, because if soil liquefies, there is an acceleration cutoff. So because of these four reasons, ground motions are inevitably different. The structural response will be different. I'm telling you straight off that on some occasions it's going to be increased locally or decreased locally for some reason that we'll reveal in a while. And this is exactly where the Eurocode is trying to put things in perspective and make suggestions depending where you're designing your bridge. A little bit of evidence, because probably, just by showing photos, I cannot convince you. Let's take a very regular, I would say even common, ordinary bridge in an area that's not even of high seismicity. This is the Wharf Bridge in Austria. It is moderate seismicity in the region, and this is a bridge of 7 spans with a reasonably high length of about 400 meters. And this is excited by two different scenarios. In one, we've got the same accelerogram at all support points, uniform excitation, synchronous excitation, as you see at the top. In the other case, we've got asynchronous excitation, which means that we did our math. We have a physics-based model for ground motion simulation. We produced how many ground motions we needed here, 2 for the abutments and 6 for the piers. So we generated 8 ground motions that have time delay, local soil conditions, incoherency, and liquefaction in this case does not apply, but overall they're very different. And we pick one point at the deck, we get the time history, and we plot its Fourier spectrum. You will see that under synchronous excitation, this point is vibrating at various frequencies, which correspond to several modes that are part of the dynamic properties of the bridge. But in case of asynchronous excitation, you will notice that there is one specific frequency here that the structure, this point, is vibrating on during synchronous excitation. And then during asynchronous excitation, this is diminished, it's 0. And the same happens with another frequency, around 5 Hertz, 0. Whereas this point vibrates in 2 other frequencies, 2.37, 3.95 Hertz. If we plot the modes, these are very nice. We call them antisymmetric modes, snake-type modes, which all of a sudden have been triggered. So, lesson learned number 1. When we excite a structure with a realistic asynchronous ground motion scenario, the structure will vibrate also on some modes whose participation factor was very small if we run analysis with a common uniform assumption. But during asynchronous excitation, they will pop up, they will wake up some frequencies, antisymmetric modes that could not be seen numerically. And because synchronous excitation is something fictitious, it does not exist in the world, whereas synchronous excitation exists in the world, this is very good evidence that we are missing something very important: the contribution and the excitation of antisymmetric higher modes. So that's a very hard lesson learned straight off about something that was, in the shadows, suppressed, because we never had the data to run bridges for realistic measured scenarios of ground motion. And if you don't really believe me about this, let me show you this little video here. So you see the same bridge. This is the response of the bridge from the top under synchronous excitation, and the response of the bridge at the bottom under asynchronous excitation. You see that as time passes, under uniform excitation, the bridge tends to vibrate out of plane. Okay, that's very visible. whereas under asynchronous excitation, the bridge aims to do a snake-type antisymmetric mode. So the frequencies that I just told you about that were revealed by a fast Fourier transformation are even visual by naked eye. The response of the bridge out of these two scenarios is very different. The one is what we normally do. The second one is more realistic because it is based on all the features of asynchronous excitation as we discussed. So this is fundamental. This is recognized. You will probably ask me here, well, Tassos, if this was known and if this was so important, why this is not in the codes? Well, the reason it is not in the codes, it is because this is a phenomenon which is quite case dependent. It is because it is difficult to ask engineers to generate ground motions that represent all the physics of wave propagation in a complex source medium. And I think most of the codes are practically avoiding phenomena that are associated with high uncertainty because there is nothing they can actually do to reduce this uncertainty. And they avoid to open Pandora's box of something that will give you very different results depending on your assumptions. It is so much easier simply to apply a safety factor or just close the eyes and move on. So no blame to the code. That's a complex problem. And the only reason that in the new version of the Eurocode, there are some specific conditions and advice on how to deal with it is because there are some concrete results about what's going on and what's the simplest way we can take it into account. So this explains why the problem is important and why the problem has been neglected in the previous versions of the code. Another example, Chalkida Bridge. This is connecting the island of Evia with the Greek mainland. It's a 700 meters bridge, cable stayed, the central deck of about 400 meters. So basically we can consider two piers here. This bridge is permanently instrumented. And during the 1999 earthquake in Athens, there were measurements on the bridge, at the base of the bridge, and in the near field. So what we actually call now asynchronous excitation was measured. And the bridge response under asynchronous excitation was also measured. And therefore, it was a very good exercise that you can find in the relevant paper to compare it with the assumption that we normally make of a uniform excitation. Obviously, in this case, the asynchronous excitation is what we have practically data from an actual earthquake through permanent instrumentation. The synchronous excitation is a numerical scenario. We just pick one of the excitations at the abutment and we apply it throughout in the structure in a uniform sense. And then we select one point, for example, this point at the deck, which is instrumented by the sensor 5T. And through this point, we take the fast Fourier again, but we plot it versus frequency and time again. So it's in a plot in the frequency time space to see how this point is vibrating in time across several frequencies. In the synchronous excitation scenario, which is a numerical scenario, I repeat, only the ground motion, the ground motion at the abutment is actually accurate. The assumption of asynchronous excitation does not exist in practice, so it's purely numerical. And therefore, we can see specific frequencies where the energy vibration is concentrated, pretty much 2 Hz and 6 Hz. Asynchronous excitation scenario, which is effectively what we measured, has an extra mode. The structure is vibrating at 4.34 Hz. This is the mode. If we look at the modes, is another antisymmetric mode. We see at the Fourier spectra, the blue one is basically the synchronous excitation. You see the fundamental mode here around 2 Hz drops. Why? The fundamental mode, the response in the fundamental mode under asynchronous excitation is dropping because the structure cannot so easily vibrate at the fundamental mode because it is obstructed by the very different nature of the excitation at different points. So the structure would like to do an out of plane, but the complex earthquake input obstructs this vibration of the fundamental mode, and on the contrary, promotes this red one peak at 4.34 hertz, which looks more like the time varying, let's say, something like as if we're holding a rope and we're moving a rope, and it would take this snake type wave propagation. So nature is mimicking the rope. The structure of the bridge finds it so much easier to vibrate like a rope because ground motions travel at a time delay, and of course they're different. So this is evidence by measured data in a real bridge under a real earthquake. And that's something that the code now takes into consideration, not only as evidence, but also as part of the solution. We'll come back to this in our next topic. And then if you have time and you would like to see an additional, let us say, implication in terms of cost and loss, you will find out, just, in the interest of time, I'll just give you the quick answer about what this is all about. So if you compare the difference in the estimate of loss for a bridge under synchronous and asynchronous excitation, you will see that not only the response is very different, but the damage is very different. And because the damage is different, the repair cost is different, and the loss is different. And therefore, the whole assessment we would do for different direction of ground motion, as you see here, around 360 degrees, and different propagation, let's say, patterns of asynchronism, that would have a great impact on loss, particularly for bridges that have a strange shape, like this Krystallopigi bridge, which is at the borders between Greece and Albania. It's a curved bridge. It is difficult to accommodate the complex motion of asynchronous excitation, and the damage pattern, if you increase the acceleration beyond the design level, can be very, very, very different. So with all this evidence, I'm hoping that at least I convince you just a little bit that this is an important topic. And now let's see what the code is prescribing today and what the code is, the new generation of the Eurocode is prescribing for the years to come. First, let me say that the US and the Japanese codes do not treat spatial variability as a problem per se. They recognize that it exists. They think it is complex. They don't touch it. And practically, they only offer for bridge design larger span lengths. So the idea is, okay, probably I'm going to have differential motion between different points. Therefore, I'd better increase the seating length of a simply supported deck if I have, which is, okay, one way to deal with it, but obviously simply supported decks do not exist very frequently for long bridges anymore. And therefore, if we consider that the connection is monolithic or there is a bearing, there is a degree of connection between the deck and the pier, the more we abstract and we disturb the bridge with asynchronous excitation, the response will be different, no matter how much we want to simplify it. So anyway, back to the Eurocode, which is taking a good step ahead. In the current version of the code, there are good news and bad news. The good news is that, first of all, it recognizes that the problem exists, even the code that we're using right now, the one issued in 2005. And it also offers a simplified approach. We'll come to that in a moment. In terms of when we should account for multiple support excitation, there is this table. This table is quite meaningful, I would say. It is practically saying that you can forget everything about asynchronous excitation if your bridge is in a rocky site A and its length is more than 400 meters, or if you are in softer soils and your bridge is longer than 300, 260, or 200 meters, depending on the soil class. You should also forget about soil structure interaction if your bridge is resting on soils in every support that do not change more than one category. So to give you the opposite example, if you have a bridge which is resting at the abutments on soil A, and in the next pier soil is B, and in the next pier soil is C, so you've changed two soil classes, then you cannot escape it. You do have to account for spatial variability. So this is a very simple rule, actually. It is backed up with hundreds of analyses of different ground motions and different bridges and different seismotectonic environments. So I have full confidence that this is pretty good table, and that's exactly why it has remained in a similar form in the new version of the Eurocode. And then the code goes one step further and is suggesting, probably in your career you have already tried this, so I'll be preaching to the choir in a sense, but I'm sure you will have found out what this actually means. But for those who are not familiar, let me say what the code, the current Eurocode 8 Part 2, is prescribing for spatial variability. Let's assume that you've got a bridge. You run your time history analysis or response spectrum analysis in the most common scenario. That's it. If your bridge is longer than these limits, then you should do 2 additional excitations with a static profile of imposed displacements. So the code is giving you some simple formulae to calculate this displacement of the ground, this dg, which is a function of the spectrum and the design acceleration. And it also relates to the length of each span. And it is advising the user to create in any finite element code, like in MIDAS or in any software you're using, a set of imposed static displacements. Abutment will start with 0 displacement. Next pier will have, the next displacement calculated by this expression, and then the next pier will have an increased displacement, and then the next pier an even longer displacement, and so forth. This is a linear kind of excitation that looks like this if you impose it, and it has a cap because it cannot exceed an upper bound. So it's gonna look like the deformed shape that you see here. And this will be called displacement set A. And then you should repeat the exercise by imposing unit displacements multiplied by the standard displacement that is provided in the code in an alternate sign. So plus minus, plus minus, plus minus between abutments and first pier, second pier, ninth pier, and then final abutment. And this is gonna look like a displacement profile of this form. Inevitably, if you impose these deformations, the structure will develop some stresses. So if you have calculated some bending moments by your inertial response spectrum analysis, and you got some bending moments from the first set and some bending moments from the other set, you can easily, take the square root of the sum of the squares and pretty much increase your design quantities. And it is very simple. Now let's think a little bit if it is accurate and meaningful or not. Problem number 1. This is a static excitation. It is the scenario of imposing static deformations. For the previous 25 minutes, I'm arguing that the main feature of spatial variability is that it triggers dynamically some modes that are not participating under uniform excitation. It is impossible to capture these modes by this static displacement because it is not accounting for the degree of triggering, dynamic triggering of each mode. So by definition, it's a static approach. It will not work. Secondly, if you've tried that all these years that this method is around, you've noticed that if you pretty much do this SRSS and then compare it with your initial design quantities that you got from your response spectrum analysis, you will see that this amplification ratio rho is going to be like 2% increase, 3% increase, 5 maximum percent increase somewhere in your structure. And first of all, this somewhere does not mimic the antisymmetric modes. And secondly, it's a very marginal, very small increase. I believe because the code drafters at the time knew that this is a method that is really oversimplified, and therefore it would be too much to lead to increases like 20, 30, 40%. So they did well by at least providing a method that was not really changing the results that much. In fairness, even though I have published myself and I have my own, let's say, reservations with respect to the physics of this approach, in fairness, at least they did something and they proposed something recognizing the problem. The solution was not very accurate, but it was the first step to raise awareness about the problem of asynchronous excitation. So until today, this is what is normally done. And also, to be fair, the current version of the code, and in its Annex D, which is informative, is providing you for a way more accurate method. It has been proposed by Professor Derkuragian and Hofer in the 90s. This is a way more rigorous approach. I'm very much in favor of it, but the problem is that you can mostly use it in the frequency domain, and it's going to be quite complicated to be used by an ordinary engineer. So it's in an informative annex. I doubt if people have actually used it. It was always easier to call somebody who is doing this job and help you, generate the samples of motion for a very extended structure. That being said, the current version of the code is, even the existing one, is very much ahead compared to the Japanese and the US codes. And it goes even further in the new version of the code. So what is the new generation of Eurocode 8 proposing for specially variable earthquake ground motions? First of all, it proposes a table. There is a magic table that I like a lot, personally, because it is like a playbook, and you'll see what I mean in a while. So if you go to Eurocode 8 Part 1, because the new Part 1 is split into two parts, as you know, and Eurocode 8 Part 2 for bridges in the relevant clauses, you will see that there is, again, this characteristic length beyond which you should be accounting for ground motions. It is not asking you now to count how many soil classes you are switching from A to B to C to D or wherever. It is just asking you to check whether the average shear wave velocity from point to point differs more than by 200 meters per second, which is easier to do and more accurate. But so far, it is actually following up on the previous version of the code. And then it is equally offering you a correlation factor that you can use for generating different response spectra at every, let's say, couple of supports. And this is pretty much how you can use it. It's a method proposed by Professor Pierre Labet, works quite well. And depending on the distance between different points and this exponential factor that is dropping faster for non-uniform soils and the like, it is actually giving you spectra that are, let's say, more different from one point to another, the longer the distance is, and the more, let's say, softer and non-linear the soils are, to say it in a simple way. And this is a meaningful, simple solution that you can use. And then the code is offering this magic table I just told you, which is starting from some scenarios and is actually asking you three things. What is your bridge's total length? What is your bridge's maximum span length? And what about your soil conditions? So if you have a bridge crossing uniform, let us say, soil conditions, or with a VS that does not vary by more than 200 meters per second, so it goes from 180 to, let's say, 350 across the bridge, this is considered uniform excitation. And if you've got a short bridge is the bridge that has a length less than these numbers, characteristic lengths, depending on the soil, and at the same time, your spans are less than 60 meters, You just do nothing. You take a nap, like the photo shows, and you don't have to account about spatial variability. Bear in mind, this is 50% of a bridge already, okay? Then, if your bridge is longer than the characteristic lengths, or if it is not longer, but you do have a long span, more than 60 meters, then you can use a simplified approach that it is given in the code. I'm going to present this method in the following slides. It's quite simple to use, and it is dealing and based on the excitation of antisymmetric modes. So it is actually following up, building upon the existing literature and the knowledge we got for the last 25 years. So there is a simplified way for uniform soils. I'm going to show you how to use it, but if you don't like it, you can just omit it and increase all design points, the design quantities by 20%, and you forget about doing anything that is more explicit. And then this magic table is saying, okay, if your soils are not uniform, so they vary by more than 200 meters per second, and the depth of the valley along the bridge is less than 100 meters, so there are no significant topographic and 2D and 3D effects. So this is, let's say, the second most complex case of simple topography but varying soil conditions. Then in case of a short bridge with a short span, with short spans, you can simply forget about time delay. The local soil conditions will be more important than time delay. Why? Because it's a short bridge. So it's a short bridge with different soils. So time delay is not very important, but soils are important. And therefore you can hack it by simply doing one-dimensional site response analysis at every support point. You will not be correlating motions from one point to the other. You will not be accounting for time delay, but that's fine. At least you will account for the different local site conditions at every support point. And you can do this. But if your bridge is long or your span is long, then you need to do multiple support response history analysis, which means you need to call a friend of yours that can generate motions that account for time delay and loss of coherency and soil conditions and the like. And therefore, you can generate samples of motions and you can run your analysis with motions that are different from one point to the other. And of course, if you don't like what I just said, in the first case, you can just do nothing and increase design quantities by 20%. If you are in the second case, long bridge or long span, you can forget about calling your friend and you can increase everything by 30%. When I say everything, I mean displacements and accelerations or in essentially bending moments and shear forces in your piers that are increased by 30%. If you think that's too much, no problem. Again, you call your friend and he's gonna or she's gonna give you a set of ground motions. You will apply 7 pairs minimum as the code is prescribing, but motions that are non-uniform, you get whatever you get the average, job done. So you have these options. On the other hand, if you are dealing with such a complex bridge where you have non-uniform soil and a very strange topography with 2D and 3D side effects, then you cannot really escape it. You need to model the whole thing as you would do in a very expensive design of a bridge. Or if you don't want to do that, you do standard analysis, but you increase your design quantities by 30%. Okay, so this is the table where you can navigate. If you want, you can skip all calculations and just apply an amplification factor. Like I said, by 50%, you are not even in the case of having to apply all this because you are short bridge, short span. And in all other cases, you've got several methods you pick from, some of which most design offices can do. And if things require a very complex analysis, you will need a consultant or somebody to help you with this. It's a very handy table, and it is also based on a simplified solution that I will present briefly in the last 10 minutes that we've got for this seminar. So bear in mind, only for uniform soils that vary less than 200 meters per second between the point of the lowest Vs to the point of the highest Vs, in these cases you can use this method. This method, just to give you a heads up, it is not solving the problem. It is hacking the problem. In what sense? It is not generating ground motions. Why? Because the problem is so multi-parametric, so complex, that with 7 ground motions, pairs of ground motions, it is impossible to capture all salient features of asynchronous excitation. Impossible. But it is dealing reversely only with the response. And the idea is actually very simple. It says, I don't know if spatial variability will be important for your structure, but I assume already that based on this table here, you're already having a long bridge or a long span. So 90% it is important. And we know from the literature that if asynchronous excitation is important, by 80% it's going to trigger higher modes. So instead of generating ground motion scenarios and giving you 100 motions to run and do probabilistic assessment and try to capture things that it's really out of your hands, let us assume that asynchronous excitation has indeed triggered antisymmetric modes. What does this mean? That the elements, the structural members that are associated with the shape of the first and the second antisymmetric mode will have their design quantities amplified because of the activation of these antisymmetric modes. And if that's the case, I'm going to give you a simple formula where you amplify the quantities, design quantities of specific structural members, not all your members throughout, only the ones that vibrate like this in the antisymmetric mode. And this is really very important because it is matching the fundamental observation that asynchronous excitation may be beneficial on average because the structure cannot vibrate at its fundamental mode, as we said, but locally is going to be critical. And this local amplification will be captured by this simple method. To cut the long story short, I'm going to give you very briefly the theory as a background because the code is actually suggesting 2 very simple steps, but just to understand where it's coming from. It's coming from this work that we've done with a former student of mine. And essentially it means, well, before you start designing your bridge, you know your target coherency. You can use a Kanaita-Jimmy spectrum with parameters depending on soft, medium, or firm soil, or you can have a response spectrum, which is a design spectrum in our case. You also have to pick a coherency loss function, anyone that matches your preferences from the literature or the mean of them or whatever you really want. This is your input. And then you simply run modal analysis for your bridge. Most probably you've already run it before you did your response spectrum analysis anyway. And you take a look at the first antisymmetric mode and the second antisymmetric mode, because this is the mode you're going to use to amplify the response of specific components. And then, again, that's the theory. I'm not getting too much in it. Of course, there is what is called an influence matrix, which means that if in a bridge I impose a unit displacement in one support, I develop stresses in all constrained degrees of freedom. And if I move another support, I develop other stresses somewhere else in the structure. And if I move another point, I develop other stresses and displacements in other degrees of freedom and so on. So all combined, they form a matrix. And then I have the modal participation factors, which, depending on the nature of asynchronism of the ground motion, are going to be increased or decreased dynamically in the system. And then there is what is called the non-dimensional spatial variability parameter psi as a function of frequency omega. So ground motion at the supports are described in the frequency domain as a function of the reference one to show how much things are changing. And after we do this, we practically calculate what is the, let's say, the scale in which every antisymmetric mode is excited. You can see here how much it looks like different frequencies are amplified, if you like, in different ways, depending on the ground motion. And having done all that, which of course, like I said, is the theory, so I'm just going to skip it, you end up with a scaling factor. So pretty much you apply an amplification of specific mode influence across the dynamic response of your structure. But because this is, of course, too complex to do in a real design case, the code is offering something very, very simple. It says you run in step 1 your modal analysis, and then you apply 2 static cases. Remember the static cases of the current version of the code, but in this case, these are inspired by the shape of the antisymmetric modes, which is a dynamic phenomenon. And on top of that, apart from applying these static profiles with the shape of the forces of the antisymmetric modes, the first and the second, you amplify them by a fixed scaling factor 4 and 2. These are numbers that we have found out after thousands of analyses that are quite realistic. And by doing so, you have a group of response quantities because you've pushed your structure with a profile of forces and you got some design quantities, and then simply you do SRSS between the conventional bending moments or shear forces that you got from whatever response analysis you did, and from this simple profile of amplification as described in the previous step. You superimpose, and this means that most of your components will end up with the same bending moments, but those who are associated with the shape of the antisymmetric mode will have an amplification which will depend on number of factors, and this is exactly what you're going to get from your simple static analysis. This is very easy to do, and it's interesting here also to see a couple of case studies to check whether it is working well or not. So let's take 2 characteristic bridges. One is the Lissos bridge, which is a seismically isolated structure in Greece. This is in the area of Thrace for the lowest seismicity in Greece, 0.16, pretty much like a moderate seismicity in Central Europe. And then this is excited by a number of ground motions, accelerations or displacements. You're using whatever finite model, element model software you want. And we're going to compare the rigorous analysis, which is calculating a sample of ground motions, and then these generated motions are used as spatially variable earthquake input, and we're going to apply the simplified Eurocode data expression to see how close we are. And similarly for the Metsophon bridge, which is a very important bridge in northern Greece, 2 many pylons and 2 abutments, as you can see here. A very challenging bridge for construction in a highly mountainous area. Like I said, in the Epirus region, again, rigorous analysis with motions that change in space and in time and are compared with a simplified version. So that's my last slide. By the rigorous analysis on the left, we've got the Lissos bridge, the seismically isolated. That's why it has 10 piers. And on the right, we've got the Metsophon bridge with 2 piers and 2 abutments. All right. And the blue one is the average, the mean of the rigorous assessment with physics-based simulation of ground motion and analysis in the time domain. And the orange one is the very simple prediction with a very simple amplification of the higher modes. And you see that not only the simplified prediction is within the mean plus minus 1 standard deviation, but it's also capturing well that for some peers, those associated with the antisymmetric mode, the response is more than 1 compared to the uniform case, whereas on some other peers, the response is reduced and the effect is beneficial. So by applying this method, you always get, statistically, you get a good estimate of those peers who are more sensitive on spatial variability. Evidently, the simplified method using an SRSS on the design quantities that you got from response spectrum analysis can never be less than 1 compared to the response spectrum analysis. That's why you always see that the orange one has a lower bound of 1. Whereas if you run a rigorous analysis, you can see the benefit of 10% reduction, for example. This will not get with the simplified version, but that's a good thing to do because a simplified method should never give you less than your response spectrum method you're using. And similarly for the other peer, you can see how well the simplified method is capturing the hundreds of analyses with rigorous derived ground motions for the Metso-Von bridge. So with that, I have concluded with this presentation. I hope I gave you an idea not only about what the code is prescribing, but also how easy it is to use your finite element model to account for a very complicated problem that it would be very hard for someone who is not dealing with this aspect of earthquake engineering to account in ordinary design processes. So I think that the Eurocode 8 is taking a significant step forward ahead of all other codes worldwide, and I'm hoping that you will not be discouraged now on to implement some of the guidance that is provided in the Eurocode 8 for designing long bridges for asynchronous excitation. Now this is the end of this presentation, and I'll be more than happy to answer your questions live in the session following. Thank you so much for your participation and for your attention.